What's going on, besties? Today we're going to be diving back into the math portion of the exam for ATI TEAS, and we're going to be talking about arithmetic with rational numbers. Let's get started. So let's start with order of operations. We all understand how to perform addition, subtraction, multiplication, division, and so on. Now it's time to explore scenarios where these operations are going to be combined and applied simultaneously. To establish protocol for executing multiple mathematical operations, we use the proper sequence known as PEMDAS. This acronym represents parentheses, exponents, multiplication, division, addition, and subtraction, guiding us through the sequence in which these operations should be carried out, moving from left to right. As we work our way through, initially we are going to address any calculations within parentheses. Next, we're going to handle exponents. And then after this, we're going to look at multiplication and division. Now, it's really important to understand that we are going to perform this by moving from left to right. Neither multiplication nor division takes precedence over the other. So if our first operation is division, we would perform that operation first. Finally, we conclude with addition and subtraction following those exact same rules. Neither addition nor subtraction are going to take precedence over the other. So if our first operation is subtraction on the left, we are going to perform that operation first. Let's take a look at an example of what this will look like on your TEAS. So our first equation is 4 plus, our parentheses, 3 times 2 minus 8 divided by 2. So the very first thing we want to do following PEMDAS is perform the operations within the parentheses. We do this by multiplying 3 times 2, which is going to give us 6. Next, we're going to move on to exponents. We don't have any, so we can automatically skip this step. Then we're going to perform multiplication and division. Remember, we're moving from left to right. So the only multiplication and division that I can see is the 8 divided by 2. We're going to perform that operation and it's going to give us 4. And then lastly, we're going to finish up with our addition and subtraction. Again, moving left to right. Nothing takes precedence over anything else. So in this particular case, we have 4 plus 6. That's going to give us 10. We're going to drop down our minus 4. And that is going to give us 10 minus 4 is equal to 6. So the correct answer for this equation is going to be 6. Let's take a look at another example before we move on to our practice questions. So we have 15 plus, parentheses, 3 plus 2 raised to the power of 2 minus 9 times 6 plus 2 raised to the power of 3. So it looks a little complicated. Hang in there with me. We're going to get through this. So first, we're going to perform the operations with the parentheses first. So 3 plus 2 is the only operations we see within inside our parentheses, and that is going to give us 5. Moving down, next, we're going to calculate our exponents. That's our powers and our square roots. So we have two exponents here. We have 5 raised to the power of 2 and 2 raised to the power of 3. 5 raised to the power of 2 is going to give us 25, and 2 raised to the power of 3 is going to give us 8. Now we're going to perform our multiplication and division, moving from left to right. So as we can see here, we only have one multiplication, and that is 9 times 6. So 9 times 6 is going to give us 54, and that'll end that portion of PEMDAS. Lastly, we are going to add and subtract, again, moving left to right. Starting from the left, we have 15 plus 25. That's going to give us 40. 40 minus 54 is going to give us negative 14, and then we're going to add 8. And that is going to give us our correct answer of negative 6. Let's start with our first practice question. Calculate the following operations. We have 5 times, parentheses, 2 plus 3 minus 4 raised to the power of 2 plus 6. So we're going to start out with our PEMDAS with our parentheses. So in parentheses, we have 2 plus 3. That's going to give us 5. So our new equation is going to be 5 times 5 minus 4 raised to the power of 2 plus 6. Next, we're going to move down to our exponents. So we only have one exponent here, right? That's 4 raised to the power of 2. So our new equation is going to be 5 times 5 minus 16. That's our equation we just did, plus 6. Now we're going to move on to multiplication and division, again, moving from left to right. So if we take a look here, we only have one multiplication. That's 5 times 5. So that's going to give us 25 minus 16 plus 6. And in our last step, we are going to do addition and subtraction, again, moving left to right. So we have 5 minus 16 is going to give us 9. So we're going to drop down our plus 6 that we have left over up here. And 9 plus 6 is going to give us 15. So the correct answer for this equation is 15. And yes, there it is. Our correct answer is C. Next, let's delve into the concept of rational and irrational numbers. So at its core, a rational number is simply any number that can be expressed as a ratio of two integers and the denominator cannot be 0, right? It's right in the name, ratio, rational. It's going to be really hard for you to forget that when you're taking your TEAS. Let's take, for instance, the number 1. It can be depicted as 1 over 1, or negative 2 over negative 2, or even 500 over 500. These examples all demonstrate various ways to represent the number 1 as a ratio of two integers. And theoretically, there's an infinite amount of ways that you can do so long as the numerator and the denominator are the same. Similarly, the number negative 7 can also be expressed as negative 7 over 1, 7 over negative 1, or even negative 28 over 4. The list of representations when it comes to negative 7 is also endless. It's clear that negative 7 is a rational number because it fits the definition of being expressed as a ratio of two integers. So what about numbers that aren't whole integers? Consider, for example, the number 3.75. How can we express this as a ratio of two integers? One way we can do this is to look at 3.75 and convert it as a fraction. That would give us 375 over 100, which is the same thing as 750 over 200. Alternatively, we can understand that 3.75 is 3 3/4, which converted into an improper fraction would give us 15 over 4. So how do we do that? What we would do is we would multiply our 3 by our denominator of 4. That would give us 12. And then we're going to add our 3 that is in our numerator, giving us 15 over 4. What happens when we encounter repeating decimals? So consider one of the most well-known repeating decimals, 0.33333333, which continues indefinitely. We signify this repetition by adding and placing a bar over the number 3, indicating 0.3 is a repeating decimal. There are countless other examples of repeating decimals, but the key takeaway is that any decimal with a repeating sequence, no matter how long, can be represented as a fraction. This is going to hold true even with sequences with millions of digits that repeat endlessly. So you might be wondering at this point, hey, Nurse Cheung, with everything that we've covered so far, including integers, finite non-repeating decimals, and repeating decimals, what's left? Are there any numbers that don't fit into this category of rational numbers? Some of the most renowned numbers in the entire field of mathematics fall into this category, and we call them irrational numbers. These numbers cannot be expressed as a simple ratio or two integers. I've highlighted a section of significant examples that you're probably going to see on your TEAS. So take pi, for example. The ratio of a circle's circumference to its diameter is known as an irrational number. Its digits extend indefinitely without termination and without forming any repeating patterns. Similarly, E, which arises from concepts of continuously compounding interest and complex analysis, never ends or repeats itself, also making it an irrational number. The square root of 2 is also irrational. You might wonder if these examples are merely exceptions, or perhaps most numbers are rational, with only a few rare irrational cases that we're highlighting here. However, it's crucial to recognize that while these numbers might appear to be exotic due to their unique properties and applications, they are not as rare as you might think. Consider this perspective. I mentioned the square root of 2 as an example, but if you calculate the square root of any number that isn't a perfect square, you're going to find yourself with an irrational number. Moreover, when you combine any irrational number With a rational number, whether it's an addition or multiplication, it's going to result in some kind of irrational number. This demonstrates just how abundant irrational numbers actually are when we're looking at the mathematical landscape. Let's take a look at our first example. Which of the following numbers is irrational? So let's break each one of these down. So we have 8 divided by 2 is going to give us 4. We have the square root of 16 also gives us 4. So we can automatically eliminate A and B as being the correct answer because remember, we're looking for an irrational number. Next, we have the square root of 15. Oh, look at that. We have a very long number, right? We have 3.87298, so on and so forth. But let's finish out. We have 2.75. 2.75 is a rational number. So out of all of the options that we have available to us, C is going to be the most correct number because there's a lot of repeating decimals, but they don't follow a pattern. Our next question states, which expression results in an irrational number? So again, we're looking for irrational. So starting off with our handy dandy calculator, we have 25 divided by 5 is going to give us 5. So we know that that is rational. We can eliminate that. 2 raised to the power of 2 is 4. That's also, again, a rational number, so we can eliminate that. We have the square root of 49. The square root of 49 gives us 7. So again, we know that that is also rational. We can eliminate that. And our last number is the square root of 3. And again, look at that. We have a very long number. We've got 1.7325050, so on and so forth. So out of all of the options that we have available to us, D is the most correct answer because remember, we have a non-terminating decimal with no repeating patterns. So when we see those kind of numbers, we know we have an irrational number. Now that we have a better understanding of rational and irrational numbers, let's discuss how we're going to order and compare rational numbers. We're going to sequence these 6 numbers from smallest to greatest with the smallest number positioned all the way to the left of our number line and the largest number all the way to the right. I encourage you to pause this video and try to arrange them yourselves before we tackle it together. Let's proceed with how we're going to get the solution once you've given it a shot. We'll utilize a number line to assist us with this task, which I've prepared for your convenience. Let's begin by examining each number one at a time. So when it comes to your T's, the best option is to plot one option at a time and convert any fraction that you have to decimals to make it easier to compare on the number line. So let's examine this process. So we start with the number -3/4. So when we do our conversion, -3/4 is going to give us -0.75. So we're going to mark it on our graph right here. Next we have 0.5. 0.5 is going to be more on the right side of our number line. Next we have -1.5. Again, looking at our number line, it's going to be placed right in here. 2/3. So again, we're going to have to do a little math. 2 divided by 3 is going to give us 0.6. And again, we add our little bar on top of our 6 because it is an indefinite 6 number pattern. It's just 6, 6, 6, 6, 6, 6, 6, so on and so forth down the line. So 2/3 is going to be right about here on our number line. Next, we have -1/2. So -1/2 is going to give us -0.5. And we are going to put that right here on our number line. And then our last number is 1.75. So 1.75 is going to be way over here to the right of our number line. So if we're taking a look at this, we've already plotted it. We can get our numbers from least to greatest. So least is all the way over here on the left and greatest is all the way over here on the right. So we're just going to move our way down. So I have the answer down here for you already. So we have -1.5, -3/4, -1/2, 0.5, 2/3, and 1.75. That is the correct answer for least to greatest with this numerical data set. So we just learned about the number line method when it comes to ordering and comparing rational numbers, but there's a lot of people that also use the stacking method, so I did want to address it in this video. So the question is asking, order the following set of numbers from least to greatest. As we know when we're looking at a number line, when it comes to the negatives, the farther away that we get from 0, the more negative it becomes, right? So what we do in this method is we're going to stack all the numbers vertically and line them up based on their decimals. So if you look here, all of the decimals are lined up so that we can compare our numbers. Now, the reason why this works so well is I want to draw your attention up here to the right of your screen. So if we're looking at a set of numbers that are lined up by their decimal points, it really helps us understand how each number is greater than or less than. So looking at our two examples, we have 5.347 and 5.582. So we have to figure out which one is greater, which one is least. So we start with the first number to the left of our decimal. So they're both 5. So we automatically, those are equal to each other. We can move on to the right. So our next set of numbers, we have 3 and we have 5. Well, is 3 greater than 5? No, absolutely not, right? So we can say that 5.82 is greater than 5.347. So it just helps kind of visualize a little bit better if this method works for you. So let's take a look back at our example here. So again, whenever I'm doing calculations with comparing and ordering rational numbers, I always want to start with our negative numbers. So I'm only going to focus on our negative 0.75 and our negative 1.5 and our negative 0.5. So let's take a look. So we start with our first numbers. We have 0, 1, and 0. So as we discussed, as we move further away from 0, the more negative the number becomes, and it also becomes the least. So based on this, we have negative 1.5. So we know that our first number, our least number out of this data set, is going to be negative 1.5. So next, we're going to move on to our next numbers. Because both zeros are equal, we can automatically eliminate those. So now we have 7 and we have 5 of our negative numbers. Again, the further we move away from the 0 on the negative side of our number line, the more least it becomes. So 7 is greater than 5, which means that negative 0.75 is going to be less than negative 0.5. So now we've moved through all of our negative numbers. We can automatically eliminate those. Now let's take a look at our positive numbers. So with our positive numbers, again, we're going to be looking at the first number. So we have 0, 0, and 1. So 1 is obviously greater. Remember, the further we move to the right of our number line, the more greater the number becomes. So we know that 1.75 is going to be our greatest number. Now we have to figure out which of these two remaining numbers are going to be greater than. So we have 5 and we have 6. Is 5 greater than 6? Absolutely not. So we can put 0.5 here and 0.6 here. So out of our data set, this is going to be our least to greatest. All right, our practice question states, arrange the following rational numbers from least to greatest. So as we know, based on our number line, as we move further to the left, it becomes more least. As we move further to the right, it becomes more great. So let's take a look at each individual number. So our first number we have is negative 3/4. So we know negative 3/4 is equal to negative 0.75. So we can automatically put that right about here. And I always just write the number on top so that way I know. Let's take a look at our next number. We have 0.5. We can go ahead and put that there. We've got negative 1.25. So negative 1.25. Next we have 2/3. So as we know, 2 divided by 3 is equal to 0.6 with a bar above it because, again, it goes indefinitely to 6 in the same pattern. So 0.6 is just going to be a smidgy over here to the right of our 0.5. We'll put 2 over 3. And then lastly, we have the number 1.2. So our 1.2 is going to go right about here, 1.2. So based on the numbers we have, we know the correct answer has to be negative 1.25, negative 3/4, 0.5, 2/3, and 1.2. Do we have any of these answers that make sense based on what we know? Yes, we do. The correct answer is going to be A. Something else the TEAS is going to test you on is comparing numbers using greater than, less than, and equal to when it comes to your rational numbers. When we perform solutions like inequalities, we're going to start to see things like less than or equal to, greater than or equal to as well. But in this particular cases, we're only focusing on 3 of them: less than, greater than, and equal to. Here's a quick tip that I want you to remember when you're taking your TEAS when it comes to less than or greater than and remembering which sign you need to use. I want you to think of a very hungry alligator or a hungry hippo or maybe even Pac-Man. They're always going to want to eat the larger number. Because I live in Florida, I'm going to use the alligator analogy. So the alligator is going to want to eat the greater number. So we have 3 and we have 5 here as an example. So is 3 greater than 5? Absolutely not, right? 3 is less than 5. So our little gator here is wanting to eat that number 5 because it's very hungry. So we're going to use the less than sign, right? His mouth is going towards the higher number. So let's take a look at our numbers. So we're comparing 0.75 to 3/4. So when we look at our number line, we have 0.75 right about here. And when we divide 3 by 4, it's also going to give us 0.75. So in this case, we can say that 0.75 is equal to 3/4. Our next example, we have -1 1/10 and 2 1/5. So -1 1/10 is going to give us about -1.1 and 2/5 is going to give us about 2.2. So is our -1.1 greater than 2.2? Absolutely not, right? So we can say that -1/10 is less than 2 1/5. Now looking at our last example, we have 1.2 and -0.8. So 1.2, we're going to plot her about right here. And -0.8 is going to go right about here. So is 1.2 greater than -0.8? Absolutely. So we're going to go ahead and use the greater than sign, as we know that 1.2 is greater than -0.8. So our question states, which of the following is not true? So we're looking for the one that's not true. So we're going to break each one of these down. So we have 3/4 is greater than 0.75. Well, if we convert 3/4 to a decimal, that gives us 0.75, 0.75. Is 3/4 greater than 0.75? Absolutely not, right? We know that this one is not true, but let's go ahead and move through everything else. So next we have -1/2 is greater than -0.6. So using our number line, we know that -1/2, when we convert it to a decimal, is -0.5, and we have -0.6. So 0.5 would be here, 0.6 would be right about here. So is -1/2 greater than -0.6? Yes, absolutely. So we can automatically eliminate that answer. So next we have 0.5 is greater than 1/3. So as we know, we have 0.5, and then 1/3 is going to be 0.3 with a little line above it. So is 0.5 greater than 1/3? Yes, absolutely. So we can automatically eliminate that. And then our last is 2.5 is greater than 5/3. So when we convert 5/3, we get 1.66, so on and so forth down the line, and we have 2.5. So 2.5 would be about right here, 1.6 would be right here. So is 2.5 greater than 5/3? Yes, absolutely. So the correct answer is A, 3/4 is not greater than 0.75. I hope that this video is helpful in understanding arithmetic numbers when it comes to the ATI TEAS. As always, if you need any additional assistance, make sure you leave some comments down below. I love answering your questions. Head over to nursecheungstore.com where there's a bunch of additional resources to help you be successful on your TEAS. And as always, I'll catch you in the next video. Bye!